All right, so before we start with the actual lecture, once more the announcement that we shifted the exercise class to a new and larger room. So all of you should have plenty of space next week. So don't go to the HIT building anymore, but to the HPT building, just next to the bus stop. Sorry? It's without computers, yeah. We asked in the first exercise class if anyone needs them, and no one did, so. All right, so hello everyone. As announced last week, Professor Troyer is presenting the CSE case studies in the center, and therefore we'll be doing a review of basic C++ to get everyone up to speed. If it's too basic for you, you're welcome to leave at any point and come back next week when I think we'll start with build systems and more advanced C++. So I'll be going with a rather high speed through a lot of different parts of the C++ language. So please, at any point, tell me to slow down or go more into detail if you want more explanation. So it's your chance to fill up all the gaps that you might still have with C++ basics. All right. So let's start very simple. Basically, the simplest program you can write in C++, a hello world. The first line shows you a comment, so it's not part of the actual program, it's just for the human reader. And comments are delimited with the slash and the asterisk. These comments can span multiple lines. Down here you see a different one, the one-line comment, which starts with a double slash and extends until the end of the line. Then the first part of the actual program is the sharp include IO stream, which includes all the declarations of the IO streams which you need to write things to the terminal or read things from there. Then there's the using namespace std, which says we want to use all the stuff that's in the standard library, which is called std. Then that's a part of the actual program. The main program is always called main. If you call it differently, then the compiler will complain that there's no main function. So the main entry point in your code is always called int main. Then here we write one line to the standard output stream, which is called cout. And this left shift operator, which is this double left brackets, is used to write something into the stream, right? Then we already had this one-line comment. Statements always end with a semicolon. If you want, you could put several statements into one line. Just by putting a semicolon after each statement, but it tends to get rather all right, it tends to mess up things, so usually it's a better style to put one statement in each line. And then last we return 0, which means everything went okay and the code successfully completed. Right. Any questions here? Okay. You could also tell me to speed up if all of you are bored to death, right? Right. More about this standard namespace. Here we have three parts, three different versions of the same code, which all are very equivalent.
It sounds like that buzzing is the audio.
Up here, we globally say using namespace std. So from this point on, we can use cout and all the other stuff which is in the standard library without saying more specifically this is from the standard library. Without this using namespace statement, we have to explicitly specify in front of each cout that it is part of the std namespace. Or we can also import only specific parts of the library by saying using std cout. Then we can use cout without the std, but nothing else from the std library.
So
in your codes, you can use any of these styles. The only important thing is if you write a library, then in the headers never put any global using statements, because that would mess up everyone's code who includes that header. So that's important.
Two pieces of code.
Within your source files and implementations, use whatever you want. So let's start trying something more useful and do some actual calculation. Here, after the IO stream header, which we've already seen, we include the CMAS header, which, as the name already suggests, is the header for mathematical functions. Specifically, we use this square root function, sqrt, from there. So here we see that we can put several things into the cout stream just by concatenating the stuff with several of these left shift operators here. And then we have some constant expressions, some literals. Here we have a floating point constant which has the value 5. And this is an integer constant. It does not have a decimal point with the value 0. And here we have a string literal. All right, so let's go through the different data types which are provided in the basic standard. So let's start with the integral data types. There's different signed and unsigned types. Of the signed types, there are several lengths, so they include a different number of bits. The smallest is the so-called short type. Then there's the integer, the long integer, and the long integer. In general, the longer version has more bits and therefore can store larger numbers. Then, since C++11, you also have some types that explicitly specify how many bits you actually want. This is implementation defined for these short int long types. So in general, you could have one platform where the short has 16-bit and another platform where the short has 32 bits. If you want to be sure how many bits you get, you can use these int 8, int 16, and so on types. Then there's the unsigned alternative of all these types, which do not have a signed bit, so they can only store positive numbers. And then all these store the number in binary format, of course. Here are the typical lengths of these standard types. It always says usually because the standard does not require a specific length. Any questions? No? All right. So how are these numbers stored in detail? In general, a byte has 8 bits. So an n-bit integer is stored as an integer with n divided by 8 bytes, right? Then the order in which the different bytes of the number are actually stored in detail is again implementation defined. There's two more or less used conventions, the little endian and the big endian. On the usual Intel x86 compatible platforms, you have little endian. If you still have a Power PC around, there you have a big endian format. And if you want, after this lecture, you can try to write a program on your own that checks what format your CPU has. Then for unsigned integers, the storage layout is very simple. If you have an n-bit unsigned integer, you have n bits, which just one after the other store the number in binary format. Nothing specific, nothing special. If it's signed, the first most significant bit is the sign bit. And afterwards, you have n minus 1 bits of the actual number. For positive numbers, the sign bit is 0, and the rest is the actual number in binary format. For negative numbers, that was already explained in the last lecture, the rest is stored in this 2's complement format. You could come up with different conventions how to store negative numbers. The advantage of this 2's complement is the same adding unit in your CPU works for signed and unsigned types. Right. So in your code, if you want to include some number, you can very naturally input this number. If you want a 0, you write a 0. The number without a decimal point is usually gives you an integer. So 0 and minus 3 would both be integer constants with a sign bit. If you specifically want a constant that does not have a sign bit, but is an unsigned type, you can put this postfix u after the number, which says you want an unsigned data type. There's other postfix for the different precisions. So you have short, s, unsigned short, us, or su, however you want. Long is an l, unsigned long, ul, long, long, ll, and all the combinations. Closely related to the integer numbers are the characters. There's a char, like character. There's a character type without a signed bit, unsigned, and one with a signed bit, the signed character. The standard does not tell you if this guy, the char, has a signed bit or not. That's implementation defined. It uses the ASCII standard. There's this white character WCHAR, which you could use for some special characters like Japanese, Chinese symbols. Unfortunately, this is not using typically the widespread Unicode standard. The new C++ standard, C++11, does have formats which require and allow you to use the Unicode standard. Constants with the value of a specific character can be entered with this single quotes. So if you write quote a quote, that's a single character with the value a in ASCII format, and so on. There are some special characters which you write by prefixing it with this backslash. There's a tabulator \t, a new line \n, the line feed \r, which is mostly used on Windows, where line break is new line and line feed. And there's the 0 byte, which is used to end a string constant, as we will see in a moment. So for strings, the usual C-type strings were C-style character arrays like this. In C++, don't use them. In C++, there's this std string class for single byte character strings, and the corresponding thing containing these white characters, W string. String literals are entered with a double quote, as opposed to the single quote for single characters. And these string literals contain a trailing \0, so a 0 byte, to signal that that's the end of the string. And that's the reason, that was one of the questions in last week's poll, that the size of this string, which seems to contain 5 characters, 1, 2, 3, 4, 5, that the size of this string is actually 6, because in the end there's a \0 implied. All right. There's Boolean types. The type is just called bool, and the literals are true or false. That's it. Floating point numbers are a bit more interesting. They come in 3 different variants. There's the single precision float, which is usually a 32-bit floating point number. There's a double precision double, which is usually 64-bit, and an extended precision, the long double, which might or might not be more precise than the double type. There's a lot implementation defined to allow each vendor to implement something fast on his architecture. Likewise, literals include a decimal point. If you only write a number with a decimal point, you will get a double precision number by default. If you don't include any numbers after the decimal point, it will still be a double precision number. If you want a different precision, you can use the F postfix for single precision and the L postfix for the extended precision, the long double type. So typically these floating point numbers adhere to the IEEE floating point representation, which demands that the layout of the actual number in the memory is divided into a sign bit, an exponent, and the mantissa. So these are the numbers for the IEEE formats. So the float type has an exponent of 8 bits and a mantissa of 23 bits. The double type has 3 more bits in the exponent and a lot more precision in the mantissa. So this float type, the single precision, gives you typically an accuracy between 6 to 9 digits. That's not much. So if you do a computation, in general, I would advise you to use the double type. And only if you really need to save memory, then you can start thinking about at some points using the float number. But by default, use the double. So we can have a short look into this IEEE representation. How is that stored? We had the sign bit. If that is 0, we have a positive number. If it's 1, we have a negative number. Then the exponent is stored without a sign bit. The convention is just that the first half of the range of this number is negative and the second half of the range is positive. So you take the exponent that you would like to store and add half the range of it. So for a floating point number, you add 127 to it. This gives you then the exponent like you store it. Like here in this example, your exponent in base 2 should be 7. Then you add 127 and you store 134 into the exponent part. That's the 134. And then for storing the mantissa, the convention is you do a left shift of the number until you have a 1 in the binary representation. And this 1 is just assumed. It's not explicitly stored. And you just store all the stuff behind the decimal point, well, base 2 point. So that's the mantissa, which is normalized and stored here. Again, this 1 point, the first part of the mantissa is assumed and not stored explicitly. Questions? I mean, you can easily look that up on Wikipedia or your favorite reference. All right. A word of caution, floating point arithmetic always has truncation errors because you always only have a finite precision. So especially if you have numbers on very different scales, then you will have huge truncation errors or round-off errors. So if here we have a precision of 1, 2, 3, 4, 5, 6 decimal places, like possibly with a float, and then we add 1 to this rather small number, then everything here will just be rounded off because it cannot be stored. Because in the end result cannot store more than these 6 digits. And so in this context comes the machine precision epsilon into play. So we define epsilon as the smallest positive number such that 1 plus epsilon in this format is not equal 1. So this exercise you already did, I think. In general, when working with floating point numbers, be careful about round off. We have an example for different ways to sum these numbers in the lecture repository, which you can have a look at. Then many times I told you typically it's like implemented like this, but in the end the standard does not guarantee how it's stored or implemented. The standard actually provides a way to check what the implementation actually is, and that's this so-called numeric limits trait, which is defined in the header limits. If you have a standard type which provides this information, then this expression, numeric limits of the type is specialized, will be true, and you can get more information. There's a lot of important information in there, most notably for integral types. You have the largest negative number min, the largest positive number max, the number of digits in base 2 and in base 10, and a lot more. For floating point types, you're typically interested in the minimum min, which in this case is the smallest non-zero positive number. The maximum, again, number of digits in base 2 and in base 10. And epsilon, the floating point precision, which we just talked about. So if you wrote a nice code to try that out, you could in the end compare to this value and check if your code is right, or maybe the implementation is wrong. Who knows? And again, much more. Here you see the first example for templates. These will be covered in depth later on in the lecture. For now, you just need to know that for using that stuff, you replace the T in these brackets by the name of the type that you want information about. So for example, you say std numeric limits, double, and then epsilon. And this expression will be replaced by the compiler by the actual value of the floating point epsilon for double precision. Right? So let's do something slightly more useful and ask the user what he actually wants to calculate. That part up here you already know. We include the I/O streams and the mathematical headers. We want to use everything from the namespace standard. Now we write to the output stream that the user should enter a number. Here we declare a variable x, which should have the type double, so double precision floating point. And then we read from the input stream, which is called cin, into the variable x. So one floating point value is read from the user and assigned to the variable x. Then we output the square root of, here the actual value of x is output is, and here the square root of x, and the end of line. Yes? Yes. So okay. So the question was, what happens if we have an evil user that does not input a double but something else? So here the I/O streams library will try to make sense of that and interpret the input as a floating point number. And if that fails, then it will throw an exception. And as we don't do any exception handling here, the program will abort. Okay, more questions? No? So we saw the first example for a variable declaration. In general, the syntax for that is type name variable list. We just saw the double x. We could declare several variables in one statement, separated by a comma. We could declare a Boolean variable named flag. It can appear anywhere in the program. That's a change for C programmers. And you can include some initializer. Like here, the value I, which is an integer, is initialized to 0. That's a C-style initializer. You can also call the C++ style constructor with these parentheses after the name of the variable. Both will have the same effect. You declare a variable, and it will be assigned an initial value, 0 or 2.5. You can declare that the variable should be const, that is constant, and that means that any try to change the value of this variable later on in your code will fail, and the compiler will say that's a constant, you cannot change it. As more advanced types, there's the so-called enumerators, which basically are integers, but you can only assign specific values within a given set. So you could declare this enumerator traffic light, which can take on the one of the three values red, orange, or green. Or this enumerator occupation, which can take any of these three values, which are named empty, up, down, or up, down. After declaring this type, you can just use it like any int or double or something. You say you want a variable called light of type traffic light, and it should be initialized to green, that value. Right? There's arrays. So for any type like int or double, you can have an array, so several variables in a row with one single name. So that's an array of 10 integers. That's an array of 100 double values. This here is a two-dimensional array of size 10 by 10 floating point values. And one notable thing is indices start from 0. So if you want the first value, you give the index 0. And the last index is n minus 1. So the first integer in here is I0, and the last one is I9. I10 is beyond the array and might give you all kinds of funny errors, which are hard to find. So all these arrays are C-style. C++ provides a lot nicer array types, which we will look into later on. If you have some complex type, then it's often very useful to define an alias, a short name for that. So for example, for that you use this typedef, which says vector 10 should from now be an alias for an array of 10 doubles. And then you can use this alias vector 10 just like any other type to declare variables. Here you see how to initialize an array just with these braces and then numbers separated by the comma. With that, you can also create even more complex types. You see this vector 10 is actually an array of 10 doubles. And here you create an array of 10 of these vectors. So in the end, you have 10 arrays of 10 doubles. So actually a matrix, and it's equivalent to this form with a 2D array. All right. Then for numerics, comparisons, so on, you have the usual operators. For doing arithmetic operations, you have multiplication, division, modulo operation, addition, subtraction, negation. There's the increment and decrement operators in two different variants. There's the pre-increment and the post-increment. The difference is the return value of this operation. So both of these variants increase the value of the variable a by 1. This one first increments the value of the variable and returns the value after the increment. This one does the increment but returns the value the variable had before it was incremented. And the same for the decrement, which goes one down. Logical operations, so mostly comparisons. Logical not, less than equal, greater than or equal, equality, inequality, logical and, logical or. some more. There's this ternary operator where A is evaluated as a Boolean expression. If that evaluates to true, then the return value is B. Otherwise, if that evaluates to false, the return value is C. And last but not least, very important, the assignment. The value of B is assigned to the variable A. Be careful, that's the assignment with one equal sign. The equality has two equal signs. If you want to check for equality and write only one equal sign, you will get rather funny and not so easy to spot mistakes. There's bitwise operations like bitwise not, left shift, right shift, bitwise and, bitwise XOR, exclusive or bitwise OR. There's a lot nicer bitset class if you want to manipulate a row of bits. We will introduce and use that later on. For all that, refer to a book if you want to know more. One notable thing is, originally these double arrows were bit shift operators. Now for I/O streams, these are redefined or overloaded to be used for input and output operations. So this thing here does not do a bit shift operation on the output stream, but writes something, the string here, into the output stream. And this operator overloading can be done for any user-defined type, which allows you, for example, to write matrix operations for your specific matrix, just like you would use it for any standard types. We'll look into that later on too. There's compound assignments listed here, which are exactly equivalent to doing the operation. So A plus assign B is exactly equivalent to doing the operation A plus B and assigning the result of that operation into the variable A. Strictly speaking, it's not needed, but often it allows for simpler code and allows the compiler to easier optimization. All right, there's a lot more operators which seem quite complicated. We will look into all of them later on in the lecture. If you have a sequence of different of these operations, then a special operator precedence needs to be evaluated. The compiler needs to decide whether to first sum two numbers and then multiply, or the other way around. For the arithmetic operators, they use the usual rules. For example, multiplication takes precedence over the addition. So this expression is equivalent to parentheses around the multiplication and then doing the addition. So you can look all that up. But if you're in doubt, then better use parentheses, because chances are high that if you look at your code a month later on, you will not remember what you looked up and you have to check again. Right. All the code is composed of statements which end in the semicolon. So the semicolon by its own is a no operation statement, which will just be optimized away. There's declarations, as we've already seen, type definitions with typedef, and more complex statements. You can put several simple statements together with braces. So here you have three simple statements, which you can put together with these curly braces, and that's again a statement. There's the if statement. If the condition is met, execute the statement, otherwise go on without doing this. You can chain them together with if condition, do this, else do that. And more of that with if that's true, do this, else if that's true, do this, and in the end, an else do that. An example is presented here. If the light is red, write stop. Otherwise, if the light is orange, write attention. Otherwise, write go. Okay. Instead of nested if statements, there's this switch statement. Switch depending on the value of this variable light. In case it assumes the value red, execute this part. In case it contains the value orange, execute that part. Otherwise, if it contains the value green, do that. If it's none of the above, do the default statement. Never forget the break after the case. Otherwise, it will just continue doing that. What's after this, even and if there's a case and this case is not satisfied. So if you did not write this break and the light was red, it would do this, and afterwards write attention, and then break only. And also the default statement is rather important to catch mistakes. There's looping constructs. First, there's the for loop, which contains an initialization statement, the loop condition, and an expression which typically is the loop increment, and then the body of the loop. So here's a simple example. You declare a loop counter integer I, which is initialized to 0. The loop is executed as long as I is less than 10. And at the end of each loop iteration, the I is incremented by 1. So this will output the numbers from 0 to 9. After the 10th iteration, which printed 9, the I will be incremented, and the condition here will be false because 10 is not less than 10. In principle, you can put several statements into this loop header here, but in general, that's very bad style. There's a simpler loop, the so-called while loop, which just has the condition and the loop body. An example is here. While the traffic light is red, do this. And last but not least, there's the do while statement, which always executes the statement at least once and only afterwards checks the loop condition. So whatever the return value of this function work to do, you will at least once print the output working and call the work function. And only after this first iteration, you will check this condition. There's the break and continue statements to change the execution of a loop. Break immediately ends the loop and continues after the end of the loop body. Continue will immediately jump to the next iteration. So here you have an example. This is would be an endless loop while true if there were not a break statement at the end, which can jump out of the loop. So you start the first iteration. If the light is red, you just go to the next iteration with the continue and start again at the top. Otherwise, you go on, start the engine. Then you check if the light is orange. Then you will skip to the next iteration. Otherwise, you will drive off. And in the end, the brake gets you out of the loop. Questions about that? No? Right. That example you already saw the last time. You have a for loop, a while loop, and a do while loop, and an endless loop, which all should print the numbers from 1 to the input that the user entered. So you ask the user. The for loop initializes the loop counter to 1, goes on while I is less than or equal n, and the loop increment is 1. And for each loop iteration, you output the value of I. So you start with 1, check the loop condition. If the user entered 0, you will immediately break and not print anything. Same here. You initialize I to 0 and use a while loop with the condition I less than n. So if the user entered 0, you compare 0 less than 0, which is false, and you will not execute anything. No output will be printed. Otherwise, you will print the result of incrementing I by 1. Here you see this prefix increment. And go to the next iteration. So that was the catch. In the boundary case where the user entered 0, you initialized I to 1. But then, because it's a do-while loop, you will at least once execute the statement and print 1. And only afterwards, you had incremented I to 2 and compared 2 less than equal 0. And only there you realize, oops, I should have stopped a long time ago. And here, written rather complicated to confuse you, but in the end doing the same thing with a while loop. While true, if I is greater than n, you immediately break. Otherwise, you output I and increment I by 1. Okay, we had that in the quiz last week. Everyone who didn't get it back then, did things clear up now? Great. There's a so-called go-to statement, which I will not discuss. There's some reasons to have it in the language, but no reason to use it. I think Professor Troy usually at this point includes the statement, anyone using it go to in the exercises will fail the course. Right. Before we go on to the more subtle topics of memory allocation and pointers, which is often claimed to be a more subtle issue, shall we make a break? All right, so let's do 15 minutes break. All right, so let's start again. Part 2 of the basics, the slightly more intricate basics. Let's start with memory allocation. There's 2 different types, static and dynamic memory allocation. Static is the easier, simpler one, which is what happens if you just declare variables like this. So these variables you declare here, x and y, are assigned some location in your computer's memory. The names just exist for you and the compiler, but they don't really exist in the program that's running. They're just some symbolic reference to the contents of some location in your computer's memory. All right, so in this case, we declared two variables, x and y. These will be placed somewhere in your memory. Each part of your memory has some address. And within the code, we know that the name x refers to this part of the memory, and the name y refers to this part of the memory. We gave the initial values 3 and 0, which are saved in these memory locations. So we already saw this column address, which gives you the address in the memory of your computer. And in C++, we have pointer variables in which we can store the address of memory locations. They are declared by putting this asterisk in front of the variable name. So int asterisk p is the pointer variable to an integer. You can initialize them with the help of this ampersand operator, which says take the address of the variable I and put the address into the pointer variable p. Let's see. So just by declaring some pointer p, just says we have a variable p which will have some contents which are random because we have not initialized it. And here we have declared an integer variable I, which will be in some other location of your memory and which should be initialized to 3. So the memory at location I contains this value 3. So now we can set p to the address of the variable I. Here we see I is an alias for the memory location with the address 4. And this address is now stored in the pointer variable p. To access the location that a pointer points to, you again use the asterisk operator in front of the variable name. This operation is called dereference of the pointer. So this says take the value 1 and write it to the location that this pointer p points to. So p points to the address 4, that part, and here we want to write 1. All right. So you might have heard that pointers are evil or dangerous, or you can crash programs with them. Well, at least dangerous is definitely true, because you can just, in principle, assign any number to the pointer variable, which the user will then interpret as some location in your computer's memory. And if you now write to that location, you can screw up a lot of things. For example, here, this 1 will point to some address which is actually not even a real variable, but sits somewhere in between these two variables. And if you now write something in that location which overlaps both of these, you will get very strange results. In general, this will, if you assign some arbitrary variable into a pointer, this will point to somewhere in your computer's memory which might be within the memory space of your program, or might be somewhere totally different. It might be an existing location, it might be not. Depending on that, the code might crash immediately when you write there, or you might just mess up some other variables which are totally unconnected to the pointer you wrote to. So that's the reason why you should be very careful with that. And the last note is just declaring a variable does not allocate memory for that. So if you declare a pointer variable, you don't have implicitly some memory location that you can then write to, but it will just point to some arbitrary location in your memory which might not be allocated. So to make really use of that, you use dynamic allocation, which is opposed to automatic allocation, where you just, by declaring an array of size 10, allocate memory of 10 for 10 numbers. This has a lot of limits, because if you only know at runtime how much memory you need, you cannot use this automatic allocation. So in this case, we want to read the size of the array from the user, and then just declaring an array of size n, where n is not given at compile time, this will not work. There's actually an extension in the GNU compiler which sometimes makes this work, but this is not standard compliant, and this will stop working as soon as you go to a different platform or a different compiler. So the solution to that problem is dynamic allocation, which uses this new operator. And for that, you need a pointer variable to save the result of this allocation. So this new float bracket n will allocate memory for n floating point values and return the address of this allocated memory. And now you save this address in this pointer variable x, so you can actually make use of it. After this allocation, you can work with the array just as if it was an array that you declared like this. And in the end, you need to free the memory again. And this you do with this delete x operator. After freeing this memory, you should not use it again in any way, because it might be reused or just given away from the program. So any use of the memory there results in undefined behavior. There's a subtle difference between just a delete, which you use for simple variables, and a delete with brackets, which you use for freeing arrays. So the simple rule is, if for allocation you used new with some brackets, then you need to use the corresponding delete with brackets to free the memory again. Don't mix these things up. Questions at this point? Great. You can declare and allocate a simple single float variable new float, which should maybe initialized to 0. now you can use the single float variable, and afterwards you do delete x. That's it. Other questions? Ah, right.
Can you allocate like a value to the array if you define it like that, like you did over there? Like, can you give them an initial value?
No. In this case, you cannot give initial values, but afterwards you can initialize them manually. Other questions? No. Okay. Sorry. So it says you need so much memory, and it reserves that memory from the virtual memory system. So it communicates with your operating system, saying, I need 5 megabytes of memory. It reserves them and gives you the location of that memory. Okay. Yes, pointer arithmetic can make things even more complicated. You can do calculations with pointers. So you can say the variable, n variables behind the variable that p points to. And this is exactly equivalent to using the bracket notation. So if p points to the start of an array, you can get the nth element with the bracket notation pn or p sub n, or just by adding n on top of the address and then dereferencing the resulting address. Note that adding an integer n increments it by n times the size of the type. So the language knows you have an array of integers, and then a pointer 2 behind the start of the array will give you the third integer within that array. So you don't need to care about the actual size of the variables. So this is not done with bytes, but with the number of variables. That's the reason why you declare a pointer to have a specific type, to have a pointer that points to an integer or that points to a double value. You can increment and decrement pointers. That does just the same as increasing by 1 or decreasing by 1 variable. Yes, again, be sure only use valid pointers, meaning you need to initialize them. After deleting an object, you may not use the memory location again. Otherwise, you get undefined behavior or catastrophic errors, which is a synonym for undefined behavior. Arrays and pointers are almost the same, but there's some subtle differences. So let's look at some examples. On the left-hand side, we declare an array of 5 integers. We step through all the 5 elements with the subscript operator and assign the value I to that. So the array is initialized to have the values 0 to 4. We can take the address of the start of the array. That's equivalent to saying I want the address of the first element within the array. And now I can output these elements here by stepping with the pointer through the array. So we start by pointing p at the first element within the array, array 0. We output that element. Afterwards, we increment the pointer by 1, meaning it points now to the second element of the array. We output that, and so on. And we break after 5 elements, so we only output valid elements of the array and do not go beyond the bounds of the array. You mean here? Here. No, so the array is something very similar to a pointer. So assigning an array variable to a pointer will take the address of the first element. So you don't need an ampersand here. So in many cases, you can just think of an array variable as a pointer pointing to the first element of the array. But the point of this example is to show the differences. All right. If you try to free the memory that P points to, the thing will crash because you have not allocated the memory that P points to with a new call. Trying to assign a different address to this array variable will not compile. So if you declare an array, it will always point to the first element of that array, and you cannot point it somewhere else. Assigning 0 to this pointer variable is okay. You can always put a different address into a pointer variable. Okay? And the same thing as this declaring an array statically would be dynamically allocating an array of 5 integers, putting the result into the variable pointer. Then we can go through this array just as we did here and assign the values 0 to 4 into this array. We can declare an alias to this pointer, so a second pointer variable which points to the same memory location. Go through the array via this second variable, just as we did here. So assigning one pointer to another works fine. We can delete P after assigning this address, because the runtime system just looks at the address, and P contains the address of the start of the array that we dynamically allocated up here. So we can now free the whole thing, although it's not the variable that we first assigned to. But after deleting the stuff once, we cannot delete it a second time. This will crash because we already have freed the memory, right? Same thing, if we try a third time, it will still crash. Again, assigning a pointer to a different address is okay. Likewise, this pointer variable is just a pointer variable, and hence we can also assign a different value here. Questions about these examples? No? All right. We can slowly go through this again. We have statically allocated this array with 5 elements. So A0 is just an alias for this memory location. A1 is then the next element, and so on. After stepping through the whole element, so now we declare a pointer P, which is another variable, but it's a pointer variable containing the address of the start of the array, which is 0. And now we can set p to point at those different elements, which we did here. Okay. For the second part, we declare the pointer variable pointer and assign it the address of a dynamically allocated array. So this new int 5 allocates 5 elements somewhere in the memory, and the start address of this array is assigned into that variable. Then we say p should point to the same location. So p will also point to this location. Now we can manipulate the pointers and step p through these different elements. But it's always the same thing. We have 2 pointer variables, and each of them points to some location in memory. Okay? Slightly similar to pointers are the so-called references. They're basically aliases for other variables. So if you like to declare variable names that span the whole line, and at some point get fed up with that and don't want to type it again and again, you declare the x as a reference to a float variable and say it should be an alias to this very long variable name for a number. And from now on, you can use x just as a replacement for this very long variable name for a number. So assigning to a reference will set the underlying variable. Different than pointer is you cannot point them to some other variable. So if you now declare a second variable y, then assigning y to x will set the original variable to the value of y, so 2. And it will not point x to this new variable. Okay. So then typically you want to write your programs in a more modular way and segment it into smaller functions. So you can declare your own functions, saying here I declare and define a new function. The name is square. It takes one argument, a floating point number x, and it returns a floating point number. That's the body of the function, what it actually does. It calculates this x times x and returns the result. So after defining this function, you can just use it like any function from the standard library. So here you ask the user for a number, read it, output the number itself, and then you call the function square with input argument x. The function is executed, replacing the value x had in here, and writes the result to the output stream. The syntax for that is formally the return type, the function name, and then the parameters in round parentheses. And then within these curly braces, you write the function body, what the function should actually do. If the function does not return anything, the return type is void. Like here, you have a function to write something to the output or error stream, but there's no result that you could return. There are several kinds of parameters. There's pass by value, by reference, const reference, and pointer, and principal const pointer. That we will look into in a second. Then there's slightly more advanced topics: inline functions, default arguments, function overloading, template functions. These will be covered later on. So pass by value is what you just saw. If you just write the parameters as type and parameter name, then the value of the parameter will be copied into a variable in that function called x. So if we look here, we have a function f, which gets an integer parameter x, increments it by 1, and outputs the result. We call this function from the main function, pass this variable a as a parameter. Then the value of a, which is 1, will be copied into this function f, assigned to x. X will be incremented, but not a. So we will output a plus 1, which is 2. And after the function completes, a will still be 1. Clear? Okay, that's very simple. The downside is if your function parameter is something very large, like a huge matrix, then you will waste lots of memory because it needs to be copied and copied all over. The solution to that is a pass by reference. We can say the parameter n should be a reference. If we now call this increment function, we will increment the originally passed variable x from here. So we have a variable x, we call increment, which takes the parameter as a reference. We increment the argument, and now x is 2. Calling this function with a constant argument does not work, because you cannot increment this literal constant 5. This will always be 5. So this will not compile. So the advantage of passing by reference is that we do not need to copy any large objects. We save memory and CPU speed. The downside is if you have such a function, eigenvalues of the matrix passed as a reference, this function might change your matrix A. It may not change it, but you don't know. That's rather uncomfortable. Therefore, there's the variant of passing by const reference, like this one, which says, I do not want to copy it, but the function is not allowed to change my variable A. So compare these three variants. This one does not copy, but allows the function to modify my matrix A, call by reference. Then there's call by value, where we copy the object, which might be expensive, but it protects us from changes of A. And there's passing by const reference, which is cheap because it does not copy, and it protects us from modifications of the matrix A. Questions? Yeah. Press the button, please.
Okay. So I think previously there was something like const double variable, and here is like type const.
Okay.
How it works, this const?
So this here says the reference, so the underlying value should not be changed. So it's basically a reference to a constant matrix. You could say matrix const reference const. Well, with references that doesn't make much sense.
The const matrix.
Const matrix reference A, it is exactly equivalent to matrix const reference A.
So it can be both.
Yes. More questions? No. All right. You can also pass by pointer, which just copies the address of the matrix M into the function. It's used a lot in C because there you don't have these references. It's not often needed in C++. The downside is that if you only want to access this variable, you always need to dereference this pointer variable explicitly. And when calling the function, you have to explicitly take the address to get a pointer that you can pass to this pointer. So that's passed by pointer. Now we can again have a look at these swap examples that you already saw last time. 5 variants for swapping a number. So we start with a call by value, call by reference, call by const reference, call by pointer, and again call by pointer. All right. I think we already saw last time that part 3 will not compile because we pass in A and B as constant references, and now we try to change the contents of these constant references. So the compiler says that's a const ref, so we cannot change it. Yeah. So the compilation is clear, right? Okay, so now we try to use it. We have a variable A and B. We call the swap1. What will we get as an output? One, two, you say? Can you explain it into the microphone?
Because inside of the function will be local copies, but they will be lost, and effectively there will be no change.
Right. So we had call by value, and we only swap the local copies within the function, but not the variables in the caller. All right. Part 2, we call by reference, pass in A and B, call the swap. Afterwards, what will the result of A and B be? Result of swap 2, any ideas?
Yeah, it will be swapped because we passed it by reference.
Exactly. So we pass it by reference, so we could change the variables of the caller. So it will output 2, 1. Swap 3 does not compile, we already know that. Swap 4, we pass in the address of A and the address of B. And now we have this swap 4. So what will the result of this be? Please, anyone?
Well, I think it won't swap because you just giving, like you're just swapping the addresses. And
Right.
work.
So we have locally two pointer variables a and b. Now we have a new pointer variable t, which gets the address that was stored in a. We assign the address that used to be in b to a, and then the address that used to be in a to b. All these are local changes, so the result will not be visible to the caller. Compare this to the swap 5, where we actually dereference the pointer a. So t stores now the value that a pointed to. We dereference a and write into the memory location that a points to the value of b. And afterwards, we write the value that used to be in a into the memory location that b points to. Okay, question? This one here? White space is irrelevant. It's exactly the same. No. You can put as many spaces in there as you want. Yes. Rather quickly, there's typecasts for converting variables with different types into each other. Probably the most used of these conversions is static cast, which basically does all the conversions that are relatively safe. So if you have a float variable containing a floating point number, and you want to store it in x, just saying x equals y will not work. The compiler will tell you that the types are not compatible, but you can explicitly request that y should be cast into an integer. The result will be that you throw away all the stuff behind the decimal point and you round down to the nearest integers. So this cast replaces this C-style cast here, which you should not use anymore in C++. There's a reinterpret cast, which is basically a huge sledgehammer, which says, just take the bit pattern that's in the original variable and store it in my new type. With that, you can do a lot of stupid things. So there's not many reasons to use it. It's used sometimes in low-level programming if you want to actually look at the underlying binary representation. You can have a look at these examples, which are also in the lecture repository. But we won't use much of that later on. There's a const cast, which can remove the const. So when I said if you pass something by a const reference, it cannot be changed, it was not quite true. The function could actually cast the constness away. That would be very, very, very bad style, so don't do that. Basically, the only reason is downwards compatibility. If you want to call a C or Fortran function, which does not know about constant arguments, then you say, okay, I know this function does not modify my arguments, but to make the compiler accept that and know that, I can cast the const away from this pointer variable d. So, as I said, there's some reasons to use it, but in general, it's a sign of bad programming design if you need it. There's other casts which will be discussed later. We're basically out of time, I guess. So I guess namespaces will be looked at next lecture, and default function arguments are sometimes useful. Yes, and that's basically today's stuff. Any questions at the end?